Hi everyone, welcome back to Biological Imaging. I'm Joe DeGeorgis. Today I want to talk to you a little bit about magnification, depth of field, and something known as the diffraction barrier. We've talked about microscope objectives before a little bit, and there are some typical magnifications like 5x, typically 5x, 10x, 20x, 40x, 63x, and 100. But there are some others. There could be, for instance, a 4x objective, or you might find a 16x objective. But typical microscopes have usually 5, 10, 20, 40, and actually 100. 63 is a unique microscope objective as well. And it turns out that there is an eyepiece that you look through in a microscope, and when we sit down at a microscope, of course the eyepiece is here, and there are two eyepieces on the types of microscopes that we have, and then there's a tube here like this, and then the microscope objective is on the bottom like this. And it turns out that the microscope is shaped like this so that you can comfortably sit at a desk and look through the eyepieces. So there's a mirror here like this, and the light information reflects off of the mirror and then ultimately into your eye. But this is just air in here. So you could have the eyepiece here, and you could just have a tube of air like this, and those are the two optical components, the eyepiece here and the microscope objective. The eyepiece itself also has a magnification, and it's usually 10x, but you could have a 12x or a 15x or a 20x. And the final magnification is the magnification of the microscope objective multiplied by the magnification of the eyepiece. So if you had a 10x eyepiece and a 5x microscope objective, you would have a magnification of 50 times. Obviously, if it's 4x, it would be 40 times. 10x would be 100. 20 would be 200. 40 would be 400. 63 would be 630, and finally 100 would be 1000x. So 1,000 times the size of whatever the sample happens to be. So, it turns out that if you had a 12x objective here instead of 10x, then it'd be 5 times 12, which would be 60x. So depending on the microscope objective and the magnification provided by the eyepiece determines the overall magnification of your microscope setup. Now, one of the problems of the light microscope is that it just has these discrete magnifications. I mean, you either have to choose the 5x objective or the 10, or you choose the 10x or the 20, and so on. You can't come up with a magnification that's in between 5 and 10, like 7.5, unless you could find an objective that was a 7.5x objective. But typically, when you sit down at the microscope, you have the 5, the 10, and the 20, and so on, and 40, and 100. So you have to pick which magnification you would like to use to image the subject matter. We've also talked a little bit about depth of field. And depth of field is the region of the image that appears in focus. So again, if we had a little dog, we had a person, in a mountain range, then we could set up the camera with a large aperture like 5.6, which has a fairly shallow depth of field. The bigger the aperture, the lower the depth of field, and the smaller the aperture, the greater the depth of field. So something like, f22 might have a very broad depth of field, and 5.6 okay. So if we have a shallow depth of field of 5.6 and we focus onto the person, then the dog is going to be out of focus and the mountain range is going to be out of focus, but the person is in focus and sharp. You have a narrow depth of field. But if you went to something like f22, a very small aperture, then you would have a larger depth of field, and in that case you might be able to get the dog, the human, and the mountain range all in focus at the same time. On most cameras, the aperture is built into the lens. So you have a camera, and then you have the lens here, and the aperture is built in here, and of course it's variable. You can adjust it. But in microscopy, what we're doing is we're taking the camera and we're removing the lens and the aperture, and we're just putting a little adapter on here that has one little lens and there's no aperture built into this adapter. So we also are doing the equivalent of removing the eyepiece so if we had an eyepiece and then we had a tube of air and then we screwed on our microscope objective like 5x, what we're doing is we're removing the objective and we're replacing it with this adapter, which is like an eyepiece, and it has a magnification. And then we have our camera. So there's no aperture here. There is a magnification. I haven't calculated it, but it's probably pretty close to 10x, like a standard microscope objective. And the aperture now is controlled by the objective. So it's fixed, it's not variable. And as a general rule, the lower the magnification, the more depth of field, and the higher the magnification, like a 40x or 100x, has a shallow depth of field. So 5 is a wide depth of field, or a deep depth of field, if you'd rather say it that way. So as we go up in magnification, the depth of field gets smaller, gets shallower. So now if we have our microscope, and I'm going to draw it with the eyepiece like this, again, just a linear microscope. And if we put something, a cell, some kind of cell on the slide, like this, when we take the photograph, first of all, the low magnification might be low enough so that the subject is completely in the field of view. That is, you can see the entire subject. And the depth of field might be very broad, from the microscope slide itself all the way beyond the cell. Everything in this area is in focus based on the depth of field using a 5x objective. So if you now move to, say, a 10x objective, and we put our cell on the slide. First of all, now your field of view is smaller because you're using a higher magnification, and now potentially your subject matter doesn't fit inside the view of the camera. So the edges are missing here on either side of the sample. Also, you would have a narrower depth of field, like just this region is in focus, but there are parts of the sample, like this part and the part that's right up against the microscope slide, that are still visible. It's just that it's out of focus. So now, in this scenario, because the light is being transmitted through the sample, you have regions of in-focus light and out-of-focus light, and they stack one on top of each other in the final image. So you end up with some sharp information, but everything looks a little foggy because there's both out-of-focus light and in-focus light contributing to the final image. And then, of course, if you went up to a higher magnification, like 100x, then first of all, of course, we said that we had our cell here, and we would, of course, have a cover slip. I didn't mean to not draw that on all of these, but you would have the cover slip. And, of course, on a 100x objective, you have oil here that fills this area in between the microscope objective and the top of the cover glass. But now you might have just a very, very thin area like this that's in focus, and the rest of it contributes out of focus light to the final image. So, and we would only be looking at a very small part of the specimen. Now you could photograph the specimen at 5x and then crop into the image so that you have a bigger image that's filled more appropriately in the image itself, but cropping it with a 5x objective isn't the same as photographing it with the 10x objective. There's a qualitative difference between those two images. So you have to pick what magnification you're going to use, you have to compose the image, and then particularly as you move up into higher magnifications, you have to decide what part of the sample you want to have in focus. So when you're focusing the microscope, what you're doing is moving the stage up and down, closer or further away from the microscope objective. So you could focus on this part of the cell, and so whatever was here would be perfectly in focus, and then there'd be other elements down here that are out of focus, and they ultimately are part of your final image as blurry light in your image, which makes it, less sharp, obviously. Or you can move this stage up, and the microscope objective would be then focused at this point. There's a fixed distance between the end of the microscope objective and where the focal plane lies for that particular microscope objective. So if you move the sample up and down, you're moving the sample through the focal plane of the objective, and so you could decide to make this region in focus, and now this part and this part are out of focus, or you could move it down to the bottom, for instance, where that part is in focus and then all of the upper part is out of focus and blurry. So as you go up in magnification, your depth of field goes down, and because you're looking at transmitted light, blurry, out of focus light is being contributed to your final image. So you have sharp information, sharp light information, and out of focus fuzzy light that both is added together to create the final image. And you have to also compose the shot to figure out what size you want the object to be in your final image. And in the case of focusing, you have to focus on the part of the specimen that you've chosen to be in focus. The next thing I'd like to cover is something known as the diffraction barrier, which is the limit of resolution of a light microscope. Essentially, if you have two objects that are next to one another and they are closer than 250 nanometers, they appear as a single object. And of course, if you have a single object, it appears as a single object. So you can't differentiate between these two ideas, and you can't see the fact that these two dots are actually two. It appears as one. And it's worse in the z direction, that is anything closer than 750 nanometers will appear as a single object. So even though you can focus up and down, you can't figure out whether these two objects are independent, because they're just going to appear as a single dot like this. So that's the diffraction barrier, and it's based on the wavelength of light. I mean physics. There are a few ways of breaking the diffraction barrier, and I'll just give you a very simple example. If you had two objects, oops, hold on one sec. If you had two objects that were one over the other, but still closer than 750 nanometers, then, as I said, it would appear as a dot if you were looking at it in the light microscope. But if you then embedded this piece of tissue in resin, let's do it a different way. You have two objects, and then you have one object like this. And now if you embed this piece of tissue in resin, you can section this and then look at the section, and you wouldn't see anything because there's nothing in this section. But then if you sectioned here, well, what you would see in the camera is you'd see a dot and a dot. I mean, that you'd see this is a dot, and you would see this is a dot. And then in the next section, you would only see the long object because there's nothing here. And then if you kept sectioning, eventually you would get to another sample that had a dot here and here. And in that way, you could differentiate between these two by mechanically sectioning the tissue and looking at the sections. But anyway, that's the diffraction barrier. Finally, I want to mention that there's two different types of microscope objectives. An older type, like a DIN objective, and the light, of course, comes through the sample and it's picked up by the microscope objective. But the lens is designed to bring the information through crossover. That is, it focuses this light to a point, and then this light ray ends up over here, and this light ray ends up over here, and for instance, this light ray would end over here, and this light ray would end here, and the one right down the middle would end here, and then you have, this is the eyepiece, which also has a lens in it, and it would bring the information to crossover as well. So let me redraw this a little bit. So if your objective, that brings the information to crossover. Then you have your eyepiece, and that brings it to crossover. And then you have your eyeball, like this, with a lens in it, and that brings it to crossover onto your retina. And somehow that's interpreted by your brain. The type of objective we have is called an infinity corrected microscope objective, and they have an infinity symbol printed, like a sideways 8, printed on the microscope objective. And in that case, the light comes out parallel. It doesn't bring it through crossover. And in this situation, this distance is critical. And some objectives are made to be 160 millimeters away from the eyepiece. Some others are a little bit longer. They might be 200 millimeters depending on the microscope. But in this case, because the light comes out parallel, you can vary this distance. And that became important for different techniques like fluorescence, where you might need to put a filter in here to collect certain types of information. So this area could be variable. You could stretch out this distance, and then, but again, this eyepiece brings it to crossover, and then you have your eye with a lens in it, which brings it to crossover onto your retina. So these are infinity corrected objectives, and these are usually referred to as DIN objectives, D-I-N. Okay, just one more point about objectives and the diffraction barrier. Since any object side by side that's closer than 250 nanometers, or 750 nanometers if the objects are one on top of each other, 750 nanometers. And both of these appear as a single object because they're closer than 250 or 750. It doesn't do you any good to make a higher powered microscope objective, because if you magnify these two objects to a higher magnification, or these two to a higher magnification, they still always look like a single object. So if you're using a 100x objective, you would see a single dot. And if you use a 200x objective lens, well, you'd see a dot, but it would just simply be twice as large because it's twice the magnification as the one imaged with the 100x objective. So because of that limit, they don't make objectives that are higher than 100x objectives. I mean, there might be one or two out there for very specific reasons, but most microscopes have a 100x objective as their top magnification, and it could be a very inexpensive 100x, like $50 on a kid's microscope, or it could be $15,000 on a very sophisticated microscope. And the difference is the quality of the optics, the quality of the glass. So 100x is the highest power microscope objective. And of course, if you wanted this dot to be bigger, then you can just blow that up in Photoshop to twice as large or 3 or 4 times as large. So you don't need a microscope objective to do that. Okay, that's today's lecture, a short one. Have a good night.